today is the generating function method. It's typically used for getting the recursion relationship and also get the orthonormalization normalization property of any special function. So for each special function, there will be a generating function. So that's what we will talk. So basically, you can get from this recursion relationship. With knowing P0, P1, how can you calculate higher order Legendre polynomials? You can get the normalization and orthonormal properties. So the generating function is a function of two variables. We represent by the symbol g, okay, at this point. So what it is a function of two variables. And in this case, for Legendre polynomial, it is this function. One over square root of this quantity, it's negative half, okay? This is a function of two variables, okay? And this function will produce a series series in T with a coefficient which is, I'm going to call this P and X. You could have written A and X, whatever it is. It's a function of two variables. So it is, something has to have a function of X, and this is power series in T, n going from 0 to infinity. Okay. So basically what we are saying is this function, for each special function there will be a unique generating function. Okay. For our Legendre polynomial, it is this one. And we have to prove, whatever, I could have called it A and X, B and X, C and X, whatever I could have called it, some coefficient, and it's a power series in T, and we have to prove that P and X, whatever this coefficient is, it satisfies Legendre differential equation. Then you know this function that you pulled out of your hat from, you know, something is really Legendre polynomial. Otherwise, you don't know whatever the coefficient is. Why should it be a Legendre polynomial, right? So somebody concocted this. Very clever. It's not easy how it is. It's been done. So this coefficient then satisfies, if we can prove all these things, right? This differential equation so if this coefficient satisfies that differential equation, then we can be convinced, okay, this is a generating function for Legendre polynomial. Then we can start exploiting this property, basically, to get all properties of Legendre polynomials, the orthonormalization relationship and all that stuff, okay? So, so right now, it's just, you know, you don't even know why somebody came up with such a function like this. So it's not trivial, I would say. I mean, so I'll first give you the proof of this. It's a lot of algebraic thing. You have to be a little bit patient before we go to the real neat stuff that we can do with all the properties. But we have to convince ourselves at least once, right? I mean, For each special function, like Bessel function, there will be generating function. Hermite polynomial, there will be generating function. And so that's what we have to, unique generating function. All right. So the way to do is, they got this, nothing. That's what perhaps mathematicians do, play with it. Take partial of g with respect to x, okay, and see what happens. Partial of g with respect to t and see what happens, okay. Simply something like that. So I can do that. Partial with respect to x, right? So I have to multiply this by minus 2t. Okay, let me write down all these things. So this is nothing but minus 2 and minus 2 will cancel, so it is t times this, right? So 1 minus 2xt plus t squared, negative 3 halves. I've got a t here, so I'm going to take that to the right hand side. I'm going to make this t to the power of n minus 1, n going from 0 to. So this is what partial of g with respect to x is giving me. So I'm going to write down this for a minute here. I need this later. All right. So this, if I write this as 1 minus 2xt plus t squared negative half I can write, I just split this, right? There's nothing but splitting that. Now what is this quantity? G, which is this, right? So I can write, I can substitute for that the following. I can write it as minus 2xt plus t squared. Is it negative 1? Yeah. Okay, so it's negative 1, so I can take it to the other side, right? Okay, let me write it here for a minute and then I'll take it to the other side. Basically it is this quantity, which is summation p sub nx t to the power of n going from 0 to infinity, which is that, right? And this is in the denominator, so I'm going to take it to the other side. So let's expand the right-hand side and then we can compare similar powers of t and come up with some expression which I'll call it as identity 1, and then we play with that a little bit. So the right-hand side is p prime nx t to the power of n minus 1. I got a summation definitely. And then the next term is minus 2x p prime nx t to the power of n. And the last term is what? P prime of nx t to the power of n plus 1. Is that right? T n minus 1 t squared. So that's what we have, and the left-hand side is this. Right. So if I compared same power, because this is equality, same power of t, let us say I want to compare the coefficient of t to the power of n, right? I mean, if I did that, I'll come up with some identity on Pn's. You'll have Pn of x is nothing but, I have to change n to n plus 1 in that second one, right? P prime of n plus 1 x. The next one will be minus 2x. P prime of nx. Right, same power of n, that is t to the power of n. The last one I have to make n as n minus 1. So the last one would be plus p prime of n minus 1 x. Do I have all the terms correctly? P prime n, p prime n minus 1. Okay, so here made n go to n minus 1. That's the term I'm looking at. Here I'm looking at n going to n plus 1. All right. So, so this is one identity I have. Okay, I mean I have to juggle all these things that I get to prove eventually this. Okay, that's my goal at this point. So let's look at the other thing that I can do. I got something like this. Let me take partial of g with respect to t. All right, so if I did that, with respect to t, I will have similar thing, minus n, 1 minus 2xt plus t squared, negative 3 halves. And then, what do I have? Minus 2x, right, plus 2t. With respect to that. All right, is my right hand side will become n t to the power n minus 1, n going from 0 to infinity. All right. So I can absorb the 2, I can cancel the 2 and take the negative sign. So I have another expression here. X minus t is equal to summation n Pn x t to the power n minus 1, n going from 0 to infinity. I'm going to write down this part also separately before I get the identity. All right, so let me have this. So as usual, I'm going to call that as that, and then I'm going to take it, this thing to power negative half. I'm going to call that as Pn x Tn. So I can write this term as what? My left hand side I can write as summation P sub nx t to the power n uh, I do have a square, that is my square root part of it, times x minus t, n going from 0 to infinity is equal to, this is in the denominator so I can take it here, n p sub nx, 1 minus 2xt plus t squared, t to the power of n minus 1, n going from 0 to infinity. Is this clear? I wrote this as 1 minus 2xt plus t squared to the negative half, and there is the same thing to the negative 1. And since in the denominator I took that to the other side, okay, and this one I called it as that, right? Substitute that, and then I have x minus t. So then we can now look at the same powers of t and see what is happening. Okay. So I'm going to erase this. I need some space. So. All right. So what does that give me? Just expanded all the terms. I got x, p, and x, t to the power of n, I can write it like that, minus summation of, separate out all the terms and look at it and examine them, n going from 0 to infinity, okay, is equal to that is nothing but summation n p sub nx is the first term, minus 2nx, sorry, we said t to the power of n minus 1 is also there, right? Okay, let me just, t to the power of n minus 1 term, then minus 2x, summation n pn x, t to the power of n, okay, I'm combining that, plus the last term would be then summation n going from 0 to infinity of n p sub nx, t to the power of n plus 1. We'll just check if I have all the terms. All right. So what do we? So what relationship can I get? What identity can I get? Something? This is partial g with respect to t, right? The first term was let me just quickly, minus 2xt plus t squared, I have minus half, I think I did take that. I was doing with respect to t, so I had a minus 2x plus 2t, right? And it's n minus 1. Yeah. So the term that I have here is, and then this was equal to, I think I missed something, let me just put that. Summation with respect to that is p and x, n t to the power of n minus 1, n going from 0 to infinity, right? That's the right hand side. So I wrote this, I think I missed something here. So this one is half can be taken out. So this is x minus t, that I do, I think. And I have 1 minus 2xt plus t squared negative 3 halves times what is it? Yeah, okay, so yeah, okay, so that was equal to that, okay, yeah, this is what I do, right? All right, so that is nothing but, I just want to, I'm just rechecking my calculation, that's all. This minus 1, in the numerator I have that square root thing, which is nothing but pnx t to the power of n, right? And that on the right hand side was summation n pnx t to the power of n minus 1. Okay? And then I had taken this to the other side, which is what I have. I want to make sure my right hand side, okay, I have x pnx t to the power of n minus pnx, okay, yeah, I got it. I thought I missed something, okay. All right, so let's compare some power of t and come up with another identity. So what do we have? We can, doesn't matter which one you pick, we can always put it in a different form. Should we compare the coefficient of t to the power of n on both sides? Okay, if you did that, then what do we get? The first term is x p sub nx, right? Here it will be negative pn minus 1x, okay? And my right hand side will be this one will become n plus 1, right? N plus 1, p sub n plus 1x I have. And this one will be the same thing, I don't need to do anything, minus 2n x, p sub n x, alright? And the last term is, I have to make n to n minus 1. So the last one will be n minus 1, pn minus 1x, that's what it is. Because I'm comparing the coefficient of t to the power of n. So when you look at this expression, what I have is, I have a negative pn minus 1 here, I have negative minus pn minus 1 there, so I can cancel that. So this will lead to, I'm going to write that and then maybe simplify and put the identity, or you can simplify here also. X p sub n x minus pn, okay, is nothing but n plus 1 pn plus 1x negative 2nx p sub nx, okay, plus n times pn minus 1x. And this negative pn minus 1x, which I'm going to cancel. Okay? Those will cancel. So I don't have to consider that. So I can cancel this term with that. So I'm getting the following. So I can also, pnx is once, I can bring that here to the other side. So what I have is 2n plus 1. If I bring this to the other side, times x pnx is nothing but n plus 1 p n plus 1x. This I've taken care of, right? Plus n times pn minus 1x. This is clear? Is this clear? Is it correct? Okay. So what is the usefulness of this identity? So I'm going to erase this, I'm going to write this clearly. So what I have is identity 2 as n plus 1 Pn plus 1x plus n times Pn minus 1x is, how did I write that? Okay. Is equal to this one. 2n plus 1 x Alright. What is this identity? This is the recursion relationship that we want actually. If I know P0 and P1, I can calculate P2. If I know P2, P1 and P2, I can calculate P3 and all. So you can set up a computer program to calculate any Legendre polynomial, P0, P1, P2, P whatever it is, P10, rather than going into the infinite series and looking at what your Legendre polynomials could be, right? So let's quickly check some things and then we'll try to prove that. So this is your basically recursion relation for Legendre polynomials. So what was P0x? Last time we got it from the series, right? I mean, for any z Legendre polynomial order 0 is 1. 1. That's constant, okay, for any value of x. P1x is the one which is linear. The other one was, yeah. This is 1. This is x. Okay. So P2x, we can calculate from here, right? I mean, P0x is 1 for any value of n equal to 0. I mean, yeah. So let's put n equal to 0 here. So we have x P0x, in this case, is n equal to 0 P1x. Sorry, I should put n equal to 1 because I need the expression is the other way around. Sorry. Because I need to go from here. So let's put n equal to 1. So this will give 2 times P2x n equal to 1, which is 0. This is P0x. 2 plus 1 is 3x. P1x. And P1x is x, so this is 3x squared, right? And so P0x is 1. So P2x is 3x squared minus 1 over 2, which is 2 factorial. So it gives you automatically also what normalized Legendre polynomials. Okay, so you can just higher order. Now that you know P1 and P2, you can use this expression to calculate other things. Okay, so that is the usefulness of that. All right. All right. This is what I need to prove. So I had, this came from partial g, one of them came from partial g with respect to t, this one came from partial g with respect to x. This expression also we have, right? This came from partial g with respect to x. So supposing I substitute for this here, I can also manipulate further. Previously we were splitting 1 minus 2x squared as, the Green's, not Green's function, generating function times something. So I'm going to do a different split. I'm going to do this in a different way. Since I have this, I'm going to substitute there and see what happens. So that generates a different relationship between the PNs. I need all those things to prove that. Okay, so if I substituted this there, I can generate another identity, which is x minus t times summation p prime nx t to the power of n minus 1, n going from 0 to infinity, all right, is equal to that. So I can write this as summation p prime nx, x times that, t to the power of n minus 1 minus summation p prime nx, t to the power of n going from 0 to infinity, is equal to n p sub n minus 1 x, t to the power of n minus 1, n going from 0 to infinity. All right. So let's compare the coefficient of t to the power of n minus 1 here. So that will give me x p prime nx. I had to make n go to n minus 1 there, minus p prime n minus 1 x. What is this? N minus 1? N minus 1. So this is nothing but n times Pn minus 1 x. Right. So this gives me yet another identity. Which is x p prime nx minus p prime n minus 1x is this correct? I have it here in a different way. This is this was with respect to t, right? Pnx and Tn minus 1. So I have it in notes incorrectly. This and I'm getting it as nPn minus 1. Let me check. So I substitute for that. Fine. X minus t, tn plus 1, so that one became n plus t, that became t to the power of n, right? So that became that, and npnx, so that is that. I have it as I have the NP and X, so I just want to make sure it is, because you will get into a lot of errors otherwise with the algebra. Identity 3 is, yeah, this is NP and X. What did I miss? XP prime minus P prime Oh, it is NPNX. It's already, I copied here incorrectly. It is NPNX. So I copied it. This is NPNX. I copied it incorrectly. Okay. So yeah. All right. So yeah. So that is that. Okay. So I generated one more. I have to generate 4 identities before I can prove this. So this was just manipulation like that. All right. Very small. Okay. Okay. This one, identity 4 is obtained by, getting for p prime and 1 x from here. So what I'm going to get is the following. I'm just eliminating that, right? If p prime n minus 1x is p sub nx minus p prime n plus 1x plus 2x p prime nx. Is correct? P nx minus p prime n plus x plus 2x p prime nx. Okay, so this gives me yet another relationship, which is the following, minus p sub nx plus minus p prime n plus 1x plus 2x p prime nx is equal to n p sub nx. Okay, is there anything canceling here? No, it becomes negative n plus 1 pnx that I can combine. I think that's all I can do. Okay, so identity 4 is simply this then. So what I have is the following. You can put everything on the other side if you want, so that you could start with n plus 1. N plus 1 p sub nx. Okay. Is nothing but that is positive, right? P prime n plus 1x. Okay, I took that one term outside. So I have minus 2x plus 2x, right? So I have a negative x p prime nx. So my fourth identity is obtained by substitute for p prime nx from identity number 1, and I get I've generated one more expression connecting pn's and p prime n's. Okay, so I'm just going to write down that. That's all I need. Now, this is the fourth identity. Minus x p prime nx. All right, I think 3 more hard, a little more of algebra, and then we'll be done. I think we'll be able to get it. I think this I don't need it more. Okay. All right, so I have all these things, and I need to get this now. With all these things, I need to prove that. That is our goal. Okay, so here, let me call this equation 1, 2, 3, 4, otherwise we'll be that, I have n times Pn minus 1x minus Pn P prime of the first derivative, P prime of nx minus x P prime n minus 1 x equal to 0. Right? I'm replacing n by n minus 1, so it is n Pn minus 1. I brought it to the other side because I really wanted to differentiate that, right? Minus P prime of nx minus x P prime n minus 1x. Okay, so that's what I have. Let me call this equation 5. And then, what is equation 3? Yeah, I'm going to multiply this by x. So that gives you x squared P prime of nx minus, almost done, x prime, x times P prime minus x, nx, Pnx. This multiplication is actually very good. Multiply x, so nx Pnx. X squared, x Pn, nx Pnx. All right. So now, all right. So I'm going to add these two equations and get rid of some of the things. Let me put also here minus so that they're all the same things. Minus x minus x minus let's do that. Minus 1. Oh, that was a plus. Yeah, that was because I put it there, so that's a plus. If this n by n, yeah. So this is p minus 1. This would have been p prime, and I brought it to the other side. And this is negative, when I brought it to the other side should be plus, okay? So when I added the two equations, this and that will cancel, so what I get is the following. X squared P prime of nx plus, what do I have? This, when I add these two, will cancel, okay? That we have x squared minus 1. Let me get that. They have the same thing, right? So I can have x squared minus 1 P prime of nx. And then these two will cancel. Then I have n Pn n times p sub n minus 1 x. That will cancel, minus nx p sub nx equal to 0. Alright, it's now beginning to something but not everything, but we can, I'll just change the sign and I'll take the derivative of this with respect to x. I'll have some things and then we are almost there now. Okay, so let me, okay, let me take the derivative of this first. So if you take the first derivative with respect to x, then that take the derivative with respect to x. So one of the terms will be x squared minus 1 p double prime nx. Okay. I have that, and then I have plus 2x. I'll change the sign a little bit later, okay? P prime nx is there. Then I have n P prime n minus 1 x. Okay, here I'll get two terms, minus n P sub nx is there, taking the derivative with respect to x, minus nx p prime of nx equal to 0, right? This is what I get, and we have other identities to get rid of all that stuff, okay? Let me change the sign quickly, and then we'll be there. This is not the expression I need. Maybe identify if I wanted, then we're in trouble, but anyway. Let me change the sign. 1 minus x squared p double prime nx minus 2x p prime of nx. Okay, all this has to become n time. It has to become what we want, right? Minus n p prime n minus 1x plus n p n x plus nx p prime of nx equal to 0. Okay, so can we use any identity? This has to become that, okay? What is the identity that we can use? Connecting p prime, n minus 1, pn, and pn prime. Pn prime I don't want to change that, okay? This we have, right? N, P, and X is there, so X is also there, is it? Okay. No, I don't want to do anything with that, right? Because that is the term I need, it is there. So I want to combine these two so that I can get it. So is there an identity on the board which is going to give me n squared P and X with that, okay? We have this. Right? That I need, it's in the right form, I don't have to do anything with that. Nx p prime of nx. So identity that's connecting p and p prime and p prime n minus 1, which becomes pn. Is it this one? If I multiply this by n, do I get it? Right? You can use this one, I think. Nx p prime, multiply this by n, p prime is equal to n squared p n x. So this guy is nothing but n squared p n x. So these two combined is nothing but n squared p n x. So what we have is then 1 minus x squared is, you got n squared p n x plus n p n x equal to 0, which is nothing but n times n plus 1. This is to convince ourselves that whatever somebody concocted function of two variable is indeed the coefficient which you had it in the power series is Legendre polynomial. We had to go through all this long-winded algebra, but we have to do it at least once to check, right? I mean, we're not going to be doing everything for every special function because it's too complicated. We're going to take it for granted. Code produced that is correct, okay? But it has been checked. I want you to look at it only from that point. It's a lot of algebra, but it's not for that. It is to appreciate that whatever that expression was given to you is not easy, not trivial. Whoever concocted that expression, it was not a trivial expression, right? I mean, they must have gone back and forth to find out what is the correct combination of x and t that they have to provide square root of half, whatever it is. They have to do all these things several times to make all the thing fit into the right jigsaw puzzle, right? I mean, so that's what I want to appreciate, not to get lost in the algebra, but just to appreciate, you know, that expression which looks so simple. Otherwise, you know, whoever created that, whoever discovered that, or you know, it was not trivial. So that is appreciation I want you to have from this. Okay. So basically they had some function, so two variables, okay, they said, started playing, let me take partial g with respect to order, and then started generating several identities, how to manipulate all these identities to get it. But then that exercise they have to do what? They must have done for different combinations of x and t, okay? So it's not that trivial, it looks like simple algebra, but it's not a simple thing, whoever discovered that. Okay, so that's the appreciation I want you to have. And so once you know this, at least you've seen it once, at least you know, it is correct, but first of all, that expression. So let's go to the interesting point now. I mean, this body detail has to be given at least for one special function. From now onwards, our starting point is some generating function for a special function, in this case, Legendre polynomial, which is square root of this function, a negative square root of this function. We are saying it produces a power series. Here the coefficient is a function, it's not a constant function, x, and power series in t, and this series goes from 0 to infinity. Okay. Now that we know this, let us get the properties, all the interesting things. Okay, so this is the starting point. All the GUI, you can forget about that, that's only for you to know this was not a trivial thing, whoever discovered that. Okay. All right, let's some properties, right? Legendre polynomial for x equal to 1 for any n. So if you have to calculate Pn for x equal to 1, all you have to do is put x equal to 1 here and see what happens. Okay. So what do we have here? 1 minus 2t plus t squared negative half is p sub n, x equal to 1, t to the power of n equal to 0 to infinity. Right? So what is that? Left hand side, what can I write? 1 plus t squared minus 2t. Is a negative half, so I think of that as 1 over all that expression, right? 1 plus t squared minus 2t is what? One plus x squared plus 2x is what? Or 1 plus x squared minus 2x in this case is 1 minus x squared, right? So this quantity is nothing but x. Can I write it like this? Okay. Okay. My goal is to get this, right? I need to extract this quantity. So I got on the right hand side a series, left hand side is a function. So can I write this as a series? Then I can compare the coefficient of t to the power of n on both sides and extract out the value of Pn1. So that's a kind of a. So what is 1 over this function? Use a binomial expression to expand it out. This is nothing but 1 plus t squared plus t cubed tn. So I can write this function as nothing but summation of t to the power of n going from 0 to infinity. So that part, left hand side is nothing but summation t to the power of n going from 0 to infinity is equal to summation So if you compare the coefficient of both sides, so we can say Pn1 is nothing but 1. here, what Pn minus 1, what n equal to minus 1, all I have to do is change this, right? So what is 1 over 1 plus t? This function, when you write it in series, is alternating series, like minus t. Sorry, all the terms are negative actually. Yeah, all of them. Is t plus. No, it's alternating. Yeah. 1 minus t. You can do the binomial expansion and look at it. Okay. Minus t cubed and so on and so forth. So this I can write it as summation minus 1 to the power n, t to the power n going from 0 to infinity. Okay. So what if I want to write the summation form, the left hand side is negative 1 to the power n, t to the power n going from 0 to infinity is nothing but summation n going from 0 to infinity p sub n minus 1 to the power n. So again compare the coefficient of t to the power n. If we did that in this case, this is p sub n minus 1 is nothing but minus 1 to the power n. So P2 is positive, I mean it sort of alternates, right? Pn1 for a is 1 for all n, whether it's P01, P21, P31, it's always 1, okay? Whereas this one seems to be changing sign, okay? So that is the property of the Legendre polynomial. So let's see, how much time do you have? Yeah, I want you to maybe do this important thing. The first time perhaps we encounter Legendre polynomials is in electrostatics. Okay. So I just want to show you, supposing you have a point charge, it's not at the origin, it's somewhere, okay. The charge is located at location, let us say r prime, from the origin, okay. And you're asked to calculate potential at a distance r. Charge is not located at origin, but you have to calculate the potential at some point, r. So what do we do? It's simply, the first thing that we do is, we have to calculate its potential as nothing but q over 4 pi epsilon naught. Whatever is the magnitude of this distance, right? This is what we have to do. This angle, let us say, is theta, right? So I can write 1 over r minus r prime as nothing but what? How do you write 1 over r minus r? R minus r prime, you know how to write, so this 1 over that is nothing but 1 over square root of r squared plus, since the angle between them is not 0, this is how you would write the magnitude 1 over this distance, right? I mean, or r minus r prime can be written like that, right? So what's the connection between this and Legendre polynomial? So I can write my v as q over 4 pi epsilon naught, right? And 1 over r minus r prime. Supposing r is very far, that's the one I'm going to pull out of the square root. I can write it as 1 over r prime square over r square, right? Minus 2r prime over r cosine theta square root. What does this quantity remind you of? It's a function, right? This is what we had just proved, right? And this looks like a generating function for your polynomial, as long as you identify cosine theta as x in that, right? And r prime over r is your e. Okay, so I can write this then as, this is what perhaps you must have come across in electrostatics, right? The charge is not at the origin, you would write this quantity you would write it as 1. What should I write it here? Based on that, this seems like your generating function for Legendre polynomial. So what should I write this as?
Cosine theta, r prime over r dn.
R prime over r to the power n, right? T to the power n, right? So that, so this is what you must have come across. You know, if the charge was located at the origin, we just you know, if the Q was here, then potential at anything is just simply that, okay? But if it's not, then you have this added thing which has the Legendre polynomials, right? Which gives you how the potential is distributed in this point. So the mystery is solved, like, you know, suddenly something looked very simple, like 1 over modulus of r minus r prime is written in terms of Legendre polynomials. You know, where it comes from is from here, because we know an expression, you know, that, you know, 1 over r minus r prime is nothing but this quantity, right? And that quantity resembles, that function actually generates Legendre polynomial. So we change that to that, right? I mean, so I'm just saying it's not, you know, it comes in electrostatics through that expression. So whatever it's called as generating function comes, you can connect to whatever you have seen previously. I don't have much time. I want to talk about orthogonal property and everything, and normalization property. I got only 5 minutes, so I'll maybe do it next time. Those are interesting things, and it just comes automatically in a very simple way. So I know the first part was a lot of algebra, but I just wanted you to appreciate why that was I did the go in detail, because like I said, just looked at it and all that. But I think it's important to appreciate that this expression is not over, discover that. I mean, that's how research goes, right? I mean, it's not. It's sometimes a lot of hard work. You have to try several times, hit and try, hit and try. It doesn't come automatically. So that's appreciation you should start, because you're going to be cases to how all these things are generated. It's not easy. Okay, let me stop here, and I got homework, so I can return that.
Could you tell us what chapters we've covered in the book so far?
Right now it's 16th, I think we are in chapter 16.
Thank you.
So it's now will be 16, 17, you know, it's more, the initial chapter was just, you know,
Right.
PDs and everywhere, right? Yours is online, so I printed it, but you're okay, just, you did correct yourself. Yeah. That one's yours. I don't know where yours went. I have to check.
Oh, that's fine.
It's there somewhere. I'm going to see where I put it now.